So this is the case. This is what we will do if we have like available data. We know what are the substance we have, but if we don't know the substance, if I didn't tell you the name of the substance, then you can't use any like values of A or B or C from this from this appendix. Then we will go to the other way, that we need to make a mathematical model in order to find these phase equilibrium conditions. Okay. How we think of these mathematical models, the first thing, or scientists, when they start thinking about this approach, they said, we know entropy, then we can use entropy as the criterion, that we can use it to describe phase equilibrium. If we recall it, chapter 4 we discussed the second law of thermodynamics. Second law of thermodynamics says for any process to occur spontaneously without any external assistance, then the total entropy change should be greater than or equal to 0. Equal to 0 for reversible process, more than 0 for irreversible process. Okay, and this delta S total was summation of delta S of the system plus delta S of the surrounding. So if we have process, if we have reaction, for example, here we have reaction, and let's assume this reaction is reversible. So the reaction will occur to a certain point, and he will stop here. And this is the equilibrium, the maximum conversion that we can obtain from this reaction. No more product can be obtained. If you have any product, this product will move or will react together to produce the reactant. So we'll have here one point. This is the equilibrium composition at which there is no change happening in the entropy. So the change is happening in the direction where entropy is increasing. So in this direction, entropy is increasing. Therefore, this is why reactant is moving or reacting together to give you whatever composition here. If you have product will react together to give you the composition here, because the entropy is increasing. But we cannot achieve 100% product, because this direction from here to this one, we have a decrease happening in the entropy. So this is the whole idea of the second law of thermodynamics. Any process will occur in the direction of increasing entropy, okay? And the equilibrium condition, the state that at which there is no change happening, this is the state that we have no changing in entropy happening. The change of entropy is equal to 0, okay? So if I give you like two cases, for example, case 1, and let's say case 2, and for case 1, I give you the total entropy change is 3. For case 2, the total entropy change is 5. And tell you what will be the direction of the process. So case 1 will move to case 2 or the opposite. So 1 to 2. Because always the process is moving from like lower entropy to higher entropy. Okay? If this is the maximum entropy you have, then it will stuck at case number 2. If you have case number 3, for example, and case number 3, the total entropy is 7, then it will move from case number 2 to case number 3. It will search for the states or the condition at which it has the maximum entropy, and it will stay like stable at this condition. This is called the like the equilibrium conditions. Clear? In order to use entropy to describe this equilibrium composition, we should know the entropy of the system and entropy of the surrounding. Not one of them. Both of them should exist, because we are comparing the total entropy change, not the entropy of the system, not entropy of the surrounding. And in order to calculate total entropy of change, we should sum the whatever happening in the system and surrounding together. And this is the problem that makes it's very difficult to use entropy like as a criterion to describe equilibrium conditions, because sometimes it's very hard to find entropy of the surrounding, and this is why, or this is the limitation of using it, and this is why we need to think of another property we must use in order to describe phase equilibrium. So again, now we need to describe phase equilibrium. We need to find the conditions, the pressure and temperature at which phase change will occur. The first option, use Antoine equation. If you don't have available information to use Antoine equation, then you need to use or make or develop mathematical model. So what is the criteria that we will use to make all of your analysis The first thing is entropy. Entropy can be used? The answer is yes. But is it easy to use entropy as a criterion? No. Because to use entropy, you should know entropy of the system, entropy of the surrounding. Sometimes we can't use or calculate entropy of the surrounding. Okay? So we can't rely on entropy of the system to make this analysis. And this is only the limitation of using entropy. Is this clear? So this doesn't mean that entropy cannot be used. Entropy can be used, but it's very difficult to use entropy because we must have enough information of the surrounding.